Hello everyone, welcome back to Module 14 of the GPU Teaching Kit. We are at Lecture 14.2, Task Parallelism in CUDA. The objective of this lecture is for students to learn task parallelism in CUDA. In particular, we're going to be learning the concept of CUDA streams and how we can use CUDA streams to efficiently transfer data between the CPU and the GPU. So far, when we transfer data from CPU to GPU, launch a kernel, and transfer data back, we're doing data transfer and computation in serial. And this is illustrated in the picture where we showed for the vector addition kernel, we will be transferring A from CPU to GPU, transferring B from CPU to GPU, do some computation, which is the vector addition kernel, and then we transfer the data back from C back from GPU to CPU. As we mark in the bottom of the picture, this particular style of transfer and compute has several problems. During the time when we transfer A and B from CPU to GPU, we're only using one direction, that is the direction going from CPU to GPU of the PCIe interconnect. And also during this time, the GPU does not execute any kernel. During the time that we execute the kernel in the compute section, the PCIe bus is idle in both directions. And then when we transfer C back from GPU to CPU, we're using only one direction, that is the direction going back from GPU to CPU, and then the GPU is not executing any kernel. Remember, for PCIe, the bandwidth is actually in both directions. So when we only use one of the directions, we underutilize the bandwidth of the PCIe interconnect. Some of the CUDA devices can support device overlap, and this allows the device to simultaneously execute a kernel while copying data between the device and the host memory. And we can discover this kind of capability by doing a device query, and we can test the property dot device overlap, and if it is true, then the device has this capability. This slide shows the ideal timing we would like to accomplish when we perform vector addition on the GPU. We would like to be able to overlap the cost of copying data to the GPU, executing the kernel, and copy data back. And the way that we can accomplish this is by dividing up the vector addition work into small chunks. The picture shows the ideal timing, and the time in the picture goes from left to right. So we divide up the vector into chunks, and we call them A0, B0, A1, B1, A2, B2. At the beginning, we will transfer the A0 and B0, the two small chunks, into GPU. And then we will start the vector addition of A0 plus B0 in the GPU. And meanwhile, we immediately start to transfer the next small chunks, A1, B1. In the next time period, since we finished the vector addition of A0 and B0 and we have generated C0, we transfer the vector C0 back. And since we have already transferred A1, B1 into the GPU, we can do the compute of A1 plus B1 and we generate that C1. At the same time, we will begin to transfer A2, B2 into the GPU. So the box
shows that during the third period, we start to have a very good pattern where we're using uh, the direction of CPU to GPU to transfer C0. We're using the GPU to compute A1 plus B1, and we're also transferring the A2, B2 from the GPU back to the CPU. And as you can see, we can continue to repeat this pattern, and during the next period, we will do the same thing for the next small chunks. The way that we can accomplish this ideal timing is to use the CUDA streams. CUDA supports parallel execution of kernels and various API calls such as CUDA main copy with streams. And each stream is a queue of operations. So we can imagine that we can send commands such as kernel launch, such as CUDA and copy into one of the many queues. And these operations or commands or tasks are who belong in different streams can go in parallel. And this is commonly referred to as task parallelism in programming languages. So let's start with the basic concept of streams. Let's start with what happens in each stream. The requests that are made from the host code are put into first in, first out queues. And we will be extending each command, such as kernel launch and CUDA main copy, with another parameter, which is the stream identifier. So all the commands with the same stream parameter will be entered into the same FIFO queue. And these queues are read and processed asynchronously by the driver and the device. The driver will enter these commands into the queues, and then the driver will also remove these commands from the queues and have them to execute in the device. So here in the picture, we shown an example where we have the CUDA main copy, device sync, kernel launch, and CUDA main copy in the queue. And we showed in the picture, we're showing the oldest command in the bottom and the youngest command on the top. So the execution will be taking the bottom CUDA main copy first, and then we'll do a device synchronization. It will do the kernel launch, and then you will do the CUDA main copy at the top eventually. The driver will ensure that the commands in the queue are processed in sequence. So these 4 commands will be executed in sequence, and one command will have to completely finish before the next command will be able to execute. Now let's look at what's happening between the queues. So now we show 2 streams, and each stream will contain its own commands. And so if we have a command with the parameters 0, it will go into stream 0, and a command that comes with stream identifier parameter 1 will go into stream 1. And in practice, there will be many streams, so we can actually have many streams in the picture. But here we only show 2 of them for simplicity. The commands in these 2 streams or 2 queues will be executed totally independently of each other. So that's where the parallelism will be exploited. In the queue, we also show this event. And these CUDA events will allow the host thread to query and synchronize with individual queues. And the CUDA event synchronization command will be a good example, and we're going to address this a little bit later. This slide shows the conceptual view of streams for the programmers. we show that in the bottom, when the host code executes a kernel launch or CUDA man copy and so on, these commands are entered into the stream queues. And we show that the CUDA man copy A0, CUDA m copy B0 are the commands that have been entered into stream 0. And so in this case, we're showing the oldest command in the queue at the top and the youngest command in the queue in the bottom. When the command reaches the top, and it can be removed by the device so for execution by the GPU. The memory copy, the man copy commands will go into the copy engine on the left, and the kernel launch will go into the kernel engine on the right. So we also show that for the copy engine, there's a PCIe up, meaning that the DMA direction is going to be going from the GPU to the CPU, or the PCIe down, that is the copy direction goes from the CPU to the GPU. So in this case, for example, the man copy A0 is a copy that will copy from CPU to GPU, so that will be executed by the PCIe down DMA. So here we show that we have these man copies and so on, and that these commands will eventually reach the top of the queue, and they will be executed by either the copy engine or the kernel engine. This concludes lecture 14.2. Thank you.